Cool. So hello, I'm Stefan Kutko, and I work for a company called Electronifie. And I'm here today to talk to you about developing microservices in Node.js using event sourcing and CQRS. Like, what the hell is that? I know at least one guy in the audience knows, Patrick over there. He's a developer who I worked with back in the day who kind of had some of these ideas. He introduced me to them. I'm like, yeah, whatever. Sounds like a lot of fluff. It's actually pretty cool. So let's get into it. First, a little bit about me. I consider myself a polyglot developer. I've written production applications in C++, Java, Python, ASP.NET, Ruby on Rails, Groovy, tried a bunch of JVM languages. And right now I'm writing Node. And I've been writing Node for probably like the last 2 years, mainly. And Electronifie is a company that just launched in March. It's a fixed income trading platform. And what's unique about it is that the entire thing is written in Node.js. There is not one line of non-open source C++ in there. We wrote a Node wrapper for quick fix, which for those of you in the financial services industry kind of know it as that's the standard way that brokers and exchanges communicate with each other. We were so adamant on not having to spin up Java services that we actually spent the time to write wrappers around all these things. Ian, our CTO over there, there's this well-known open source Java library called OpenGamma, right? It implements all these functions that you can use to do bond math. We didn't want to use Java, so what do? Well, we wrote it in Python, and we also wrote it in Python because we found a couple of bugs in it that were giving some bad results, and then we wrapped Node Python, we forked Node Python, and then we wrote Python code so that we could drive all of our services from Node. So it wasn't an easy feat, but we did it nonetheless, and I'm here to talk to you a little bit about that story. So it all started when these two guys contacted me one day on LinkedIn saying, hey, we're starting a new broker-dealer. We're going to be developing a fixed income trading platform, and we need a lead developer. I worked at another broker-dealer in the equity space for probably the last 7 or 8 years. So I was pretty familiar with like how the technology is built, but fixed income is like a brand new domain for me. So I talked to these guys, I had a good meeting, and they're like, yeah, seem pretty laid back. They actually looked like this. I took this photo pretty recently, but it was like, this is what it was like me looking into Ian's face and Amar's face, and they're just like, one's a Goldman Sachs trader, one's a Credit Suisse trader. They've been trading for about 15 years. They know the business, but they needed someone to write the code. So, what? They asked me, how would you like to build it? And I don't know if anyone's ever sat across from like a couple of bond traders who are about to fund a company and say, build whatever you like, but it feels kind of like TI, the music video. Yeah. So, yeah, I'll let that run a little bit. It's a good feeling, right? Because I came from a world where there are architecture committees, there are rules, there are compliance, there's procedures to be followed. Everything was like a fight just to get it done. And in my previous place of employment, I got lucky because I had a pretty open-minded company who was willing to hear my ideas. But I remember having to pitch the idea of building websites as opposed to like thick clients in C++ for internal applications. Like, the amount of time it takes for you to just to like wire up a click handler in WTL compared to like what it's like to build a website is bar none, like in the interest of the company to do that. So coming to a brand new platform where there's virtually zero code written, do whatever you like, it's a pretty good deal. So I took it. But there are some stipulations, right? It has to be performant, resilient, maintainable. No problem. Right? Sure. Okay, so now I want to show you what we built. We started this in March, and our stack is using Meteor.js on the front end. It has a distributed microservices backend. It's using this persistence scheme called event sourcing, which I'll talk about in depth. And it also is using this other architecture technique called command query responsibility segregation. So I'm going to flip over here, and this here is Electronifie. You'll notice that it's actually a desktop application, and there's this phenomenal company called OpenFin, and what they did is they took Chrome, they forked it, and then they give you JavaScript handlers to be able to control the windows. So this is actually a web application, but the browser that it's running in is kind of this fork of Chrome that I can control. So for instance, if I want to launch a new window, I can do that. I can drag this around. If I want to sweep the book and buy some bonds, I can go ahead and do that. That's how the platform works. It's a trading application, soon to be rolled out to one of the largest many of the largest institutional investors in the United States when we get ready for launch. But the coolest thing, the thing that always impresses me is the fact that I can right-click and I can inspect element, and now I have Chrome development tools. And I don't have to support IE or Firefox. I can literally, this is like the holy grail of development. You know, there's about 1,000 people in the world who will probably have this installed on their desktop, institutional investment managers. They all run Windows, and I have the latest version of Chrome controlled. I can control screen sizes, resolutions, everything, and then I have the debugger too. So just to show you something else too, because developing in a Windows VM running on a Mac inside of an OpenFin container is a little bit tricky. What I did is I wrote this lightweight wrapper that is literally using the same views, but you'll see that it's actually running in a browser. And the funny thing is, using Meteor, which I was surprised about, it actually works in IE9. So it's this real-time messaging framework, on the front end, data on the wire, but it's really the back end that I'm going to talk to you about today. But I just kind of want to give you the visual about what this thing is and how we built it, and we'll come back to it once we get going. Okay. Microservices. So I hear the term a lot, maybe you've heard a lot too, but if I had to sit down and build an app from scratch, simple app, this is what I would do. I built an Express app with a REST API, and since I'm working in finance, we'll say, okay, it has users, accounts, orders, treasuries, and bonds. Something like that, right? These are my objects that I'm going to all persist in the database. What Microservices says is, don't just mix those up into like one big ball of mud. Instead, separate it out into like small logical services, right? So maybe I'll have an account service, and that account service is responsible for managing users and accounts. And then the market service is responsible for managing orders and trades. And then the reference data service is responsible for managing bonds and treasuries. And then instead of, if the market service needs something, it actually goes to another service and asks for it, right? So I think the kind of the mysterious thing about this whole picture is, when you go from something like this, which is very clear, because it's like one process running the entire business logic of your application, to something like this, it's like you all of a sudden have this problem where you have to kind of coordinate the movement of data around all these different services, right? So the real question is, what the hell is that thing that sits in the middle and connects all these guys together? So we could make them all individual Express apps that communicate using REST, but kind of like once you start doing that, it's like every time you add a new service, you have to go to every other service and then start like figuring out what host and port it's running on, and it kind of becomes an infrastructure nightmare. Like I've gone through various things like this where you have to make port requests and firewalls and think about servers and host names and addresses, and you don't want to do that. We just want to build apps. But then also, how do other services get notified of changes? So if I go back in here and I change something in the account service, oh, that's great. Maybe it's persisted to this user's record. But what if, like, market cares about the fact that a user is now disabled for trading? and it wants to cancel all of its open orders, right? Like, these are real problems that we have to deal with. So the question is, how can I get these things to communicate with each other? So to start from something that hopefully a lot of you have seen if you've programmed Node.js is Node's event emitter. And it's a really nice piece of functionality that says, okay, inside of a single process, what I can do is I can have different files, different classes, different objects, and they can emit events. And it creates this like nice technique, this way of loose coupling. So in this example, I have a worker, and if you don't know how to do like prototypical class inheritance in Node, here's a nice example of it. These slides will be available, so you can like look through this and see how to do it. And these are kind of like the same terms that we use. So we say worker calls the constructor of event emitter, it extends the event emitter essentially. And when you call do stuff on worker and it's finished, it emits this event done. And then what that allows me to do in a different file is now what I can do is I can start my worker, I can register a callback handler, I can tell the worker to do stuff, and then go on and do some other stuff. When the worker's finished, I just get this event. So it's really nice decoupling of domains. But the problem is that I can't use the event emitter to talk between processes. I can use the event emitter to talk within a single process, but it doesn't help me when I want to set up this distributed system where maybe certain processes are running on different boxes or even different geographies, right? So there's this nice library out there called servicebus, and it implements functionality to do very simple messaging. Three things that I found most useful about it are the ability to do a send listen. So these are fairly standard messaging patterns. Actually, these images are taken right from the RabbitMQ website. So if you go on there, they have nice tutorials about like how to do different patterns and how to do it. I highly recommend it. We're using RabbitMQ. It's written in Erlang. It's open source. A great messaging broker. So send listen. Send listen says, one process, I want to send something to someone else in only one target. It also lets us do pub sub. Pub sub means I want to send one message, but I effectively want it to fan out or broadcast to everyone who might care about it. I don't care who receives it, but I want more than one people. I want each person to get their own copy of the message if they care about it. And then kind of like an extension of send listen is worker queues. I want to have more than one process listening to one stream of messages, essentially do load distribution, right? So the code in servicebus is surprisingly simple. Like the reason why we like this library and why we use it is just because it's so easy. And you read it and it's so obvious what's happening. It works exactly like event emitter. So to do a send listen in servicebus, I require servicebus, npm install it. You have to install RabbitMQ, but if you just yum install RabbitMQ or apt-get install RabbitMQ, whatever, it's on your box, it's running fine. And then you create an instance of the bus, you point it to your RabbitMQ, then you do like bus.send, order.create. And that's essentially the channel that another process can listen on. So now all of a sudden, I have two processes that are sharing things kind of like the event emitter. It's really clean because I can have one process responsible for one thing and another process responsible for another. And there's like virtually no configuration required to get this working on the box. It does cool things like, this act equals true. So particularly for our type of applications like financial trading, if, for instance, process 2 goes down and there's like an order that someone sent but it never got a response, it actually gets persisted in RabbitMQ so that when the process comes back up, it gets that message back. And you're not going to lose anything. So it's guaranteed messaging. In order to support that, you have to call this message.handle.ack or message.handle.reject. If someone's trying to send you like a bad message, you call reject on it enough times, it goes into an error queue, you don't have to deal with it. So that's servicebus send listen. Pub sub is identical, right? Instead of a send, you do a publish. Instead of a listen, you do a subscribe. But the key is I can have multiple processes subscribe to the same command. So if this were a send-listen type scheme, what would happen is the first time broadcast is emitted, this guy would get it. Then the second time broadcast is emitted, that guy would get it. And it would just round robin between the two. But because it's a publish, now both of them get it at the same time. And in this case, I implemented like a simple heartbeat example. Both of them are sending back to the process manager the fact that they're online. So this is something that we built to kind of manage this. Yeah, question? Yeah, so I think it was like Microsoft or someone like built this. They invented this term called like the service bus pattern, which is this idea there's this like super highway of information flowing through like your message streams, and you can just like tap into there and get any messages you want. So it really abstracts that pretty well. It's really a wraparound AMQP, and AMQP is sort of like the standard queuing protocol. RabbitMQ implements it, but there's also things like I don't know if ZeroMQ does it, but we looked at some of these things, ActiveMQ. There's also Stomp protocols. It's really an AMQP. It's a wrapper on top of AMQP. Yeah. The question was, like what's it a client for? Is it a client for RabbitMQ, or is it a client for something else? Question.
Related to that, what was your reasoning for choosing RabbitMQ as like ZeroMQ or Kafka or something? No expert, but
yeah.
Curious myself.
So the question was, what was our reason for choosing RabbitMQ as opposed to like ZeroMQ or Kafka? RabbitMQ was just easy. It was easy to prototype. It was easy to get off the ground. There's a lot of literature out there on it. One thing to also notice is that I'm a very big believer in using the right tools for the job. So in the corporate bond space, it's not like the equity space. There's no such thing as high-frequency trading for bonds. That's a concept that only exists in equities. So the latencies that we have to meet are like, we talked to a counterparty recently. They have an algo engine, one of the largest banks in the world. They said, as long as you respond within 1 second, you're cool. Sure, like anything. This thing responds in like 50 milliseconds, if not quicker. We like RabbitMQ because it was free, it was open source, it was easy to configure. It's implemented AMQP, and it gave us persistence, clustering, right out of the box. It's sort of like, here's my thing. If I find something I like, I'm not going to go searching to see if there's something better. I'm going to use it until that thing doesn't meet my requirements. Then I'm going to try to go and address it, right? I have better things to do with my time, right? Like building CQRS systems. So a whole vendor enterprise evaluation of what type of messaging platform to use. Look, if it's open source and it's good following, chances are, it'll do the trick for you. We're not doing rocket science here. It's pretty common stuff. You good? All right. So if you want to think of it, like I really love Legos. So I like to think of these microservices as like these like little Lego pieces that you can put together. On one side, they take commands in, or they take events in. On the other side, they spit commands out or publish events. They can also implement query APIs. So if I want to say, I want to just get some information out of the microservice, I want it to deal with its like whole messaging architecture, you can do that. But then it also will typically have a persistence layer. Something for like just like doing graphics rendering or video processing might not have persistence. It'll just probably be like a stream of stuff. But in our case, we're persisting a lot of data. And I wanted to talk about that because I think that that's where event sourcing really shines in these types of like distributed, real-time, transactional systems. So before I move into event sourcing, any questions on microservices? Yeah?
Did you find that there still needs to be a central brain of some sort that knows about all these processes, like a higher level thing?
The question is there like a central brain that knows about all these processes, like a higher level? The answer is yes. Not by design, but because like naturally there's like there's like the alpha microservice of the pack, you know? That's like where the core logic is. In our case, it's this thing called the market service, which is actually doing the trade executions. And that thing has really become kind of like the center of attention for us. So, you know, we really drive like our workflows around that service, but I didn't realize it. Like we just built it as one thing, and just as we kind of started solving more and more problems with technology, the market service became like the governing thing. That's the thing that we scale across 32 CPUs. You know, none of the other services we scale like that, but it's also our critical path. So it, you know, that's what I like. It's very organic. It feels like this like growing thing, which is kind of cool. Question?
Is there a reason you went with message queuing and not, let's say, the pure REST architecture where you have like a sort of pub sub, then you have like request response, and anytime a service wants to pull from another service, just post a request, and then that's how you can handle caching and crashing. Is it a performance issue?
I wouldn't say it's a performance issue. I think it's really more of like a maintainability issue. We'll get into it because, you know, I'm not sure if the slides really like go into all of the issues, but one of the things that we're doing, the way that we're scaling our trading application is we're assigning certain ranges of bonds to trade to certain instances of services. And so the problem with REST and HTTP in that case is that you can only make one call to one service, right? And then either that service has to broker it to the correct service, or it has to return the data itself. And you know, it's just like it's a lot to build, you know, right off the bat. When you know, like as we start getting into like event sourcing, it's you know, we're taking a little bit of a different approach to solving this problem. So hold on to that. Like, let's talk about that after, because I think, you know, you'll see what we're doing, and it's like it might blow your mind. Okay. Sorry. How cool is it that we're at Spotify? I mean, I listen to these like unplugged, you know, Alt J or like whoever the Kooks played here or something like that. You know, it's awesome. So thank you, Spotify, for having us here. Okay, so event sourcing. I'm going to compare it directly to CRUD or REST, right? How you typically build a REST system. So the domain that we're talking about is a trading system. And in a trading system, there's this thing called a market. And a market has orders, and a market has trades. So a market can accept new orders, and when two orders, like a buy and a sell, come together at a price that can cross, it creates a trade. So if I had to go and build this in a REST-like fashion, I would start up an Express server. I would build an API that says like HTTP post/orders. I would build like a AJAX client or like a rich client that can like post something in, and I would use Mongoose, right? We got the Mongoose guy here. So you know, I use Mongoose just to create that object, validate it, save it to my DB, wait for the response, and then I return it back to the client. Okay. So the one thing I want to call out here is that when we posted the order to the system, we actually got back some like server managed state. And I think that's the key. That's really what like makes this event, you know, this sort of like, you know how I said like I don't really try to challenge things if they're just sort of working for me, but you know, this state here really wasn't working for me. It's like, geez, you know, that could change any time. That could change 100 times in a second. And you know, those updates need to get to the client because it's going to affect what they can do with that order. If they get filled, they can't go and modify it, all kinds of stuff. So just note that there's this client state and then server state. It all gets returned. That was one database transaction, by the way, insert. So let's make a CRUD trade. So now we accept a new order. Trader 2 comes in, they want to sell 20 million, the Verizon 21s at $99.95. So there's already a buy order resting in the market. A new sell order comes in. And what happens? Well, the first thing is when the order comes in, we first query for all the existing orders that are there. We can go to the cache, sure. But the point is we need to get all the orders out of the market. And then we found the fact there's a buy order, we run some business logic, we say, cool, we can make a trade and make some money, right? So we're going to create the trade. So the way that we do that is, well, first we have to record the fact that order 2 entered the system, so there's one insert there. We have to record the fact that order 1 and order 2 traded with each other, so there's a new object that we have to write. There's another insert there. But then we have to go back to order 1, and we have to update the state, and we have to say, okay, order 1, you've been filled 200,000. So in that one transaction where I accept a new order, I did one find and 2 write operations to the database. It doesn't seem like much, but imagine a world where you have like 20 orders, and you have 1,500 markets, and you're trying to keep server costs down. You don't want to like buy all this hardware and stuff like that, and you know, it starts to add up, and these things are happening several times a second. You know, we want to try to, the database is obviously going to be like the slowest part of the system, other than like network latency. So we really want to try to protect it and not have to write to it unless only very, very necessary. And so that's where this event sourcing helps out. So if we look inside of the database in a CRUD-like model, what we get is, okay, you guys seen this, right? Like, it doesn't matter if it's Mongo or SQL or whatever. You know, there's orders with IDs, there's a trade with an ID, and you can join them, or maybe a copy of the order is embedded in a trade, whatever. You know, but it's the current state of the world as we know it is persistent in the database. But that poses a problem for us, because what happens if, before order 2 came to the system, trader 1 decides to modify the order a few times, right? Maybe they change the price, they go up to 96, 97, 98. You know, the only thing we're recording in the database is just the latest state. So we don't know the fact that that trader has actually modified that order. So how do we solve that, right? Well, what I do, and you know, the most brute force attack is to just put a create add and updated add on it, right? How many people have done something like this, right? You're saving objects, you're just like, I think it's important to know that it was updated at some point. I'm not really sure why. So what you do is you just go and stick these fields on there, hoping that one day it's going to miraculously like save your business or enterprise, right? Like you're going to generate some report, aha, they updated an order, and it's going to solve all of our problems. You know, and that's great, and most of the time that works. And honestly, for simple systems, this is what I do. I don't bother capturing everything. So, you know, we know when the order was created, we know when it was last updated, so you can kind of have an idea about like what the time frame is that you're dealing with. But you miss the interim modifications, and for us that's important. We want to know, we have all this like surveillance and anti-gaming logic, so we need to know when like a trader tries to like, you know, tick up a price or tick down, or they're trying to like move a limit with the market or away from the market. Like these things are significant. And we also don't know like what the original limit price was. So, you know, $9.98, so what did this thing start off at? Who knows? So another solution that I've seen is actually to build a full-blown audit table. How many people have seen this approach? Right, this is like, you know, you get to talk to your DBA, it's like, perfect. I have a solution that requires no code on your end, but I have to write a ton of SQL, and we have to renew our license with Oracle for another 3 years. That's going to cost the company another $2 million. It's perfect, right? Like, so, you know, you can use a trigger, or you can actually like use like, there's a Java Hibernate package that I've used that actually does this for you. And what it does is essentially every time you write to the database, you're just going to save a copy of that thing, right? And it doesn't matter how it gets done. The point is like, you know, you keep a version number, and that now I know, cool, I've solved my problem, right? I know every single intermittent change that's gone on in this order. But, and you know, the only reason I say this is because I actually had a year-long project where I had a system like this, and I had to reverse engineer why the order had changed, right? The company had decided that it was important for them now to know that, oh, okay, you know, we want to know what happened that caused this change. Was it a trader? Was it a market? Was it, you know, what happened? So I built this amazing tool that, you know, was great, but it ended up getting thrown out when they actually fixed the problem and they used more of an event-driven architecture. So, the real issue is that, I see that the order has changed from 95 to 96, but if I'm writing code to go and find that, I have to do this look ahead, look back logic, go back one version, go up two versions, where am I? And then that's just orders. What if I want to glue in trades and all this stuff and try to splice the times? It's a mess. Okay. Also, not to mention the fact that now I'm just doubled the writes to my database. Every time I update the order, I have a second one. So this precious resource that we don't want to abuse is getting kicked around. Okay, so this is where event sourcing steps in. Event sourcing says, screw current state. I don't care what the state is, right? All I want to do is I'm going to maintain an immutable event log. That's important. Because once you record an event, that event never changes. An immutable event log that represents a single source of truth in the system. So instead of recording the fact that here's order 1, and then 5 minutes later here's the new state of order 1, all I'm doing is I'm recording the events that actually occurred that caused the change in order 1. And here's the thing that's going to blow your mind. It has a perfect audit history, right? Think about it. Every change in the system that goes in and potentially affects a bunch of objects, you can recreate that because you know every single event, from the beginning of time, that caused the system to get that state. I'm thinking about this feature that I want to build, which is a scrubber. During a trading day, I want to see exactly, regardless of how many microseconds or milliseconds, every incremental change for a market, so that we can potentially protect our investors against gaming. We can answer surveillance questions, we can troubleshoot issues, we can see exactly what's going on. And it's possible with event sourcing because I have every single event, no matter how quick they occur, and I know exactly what changed. Events don't have to send in copies of all the data. They just have to say, hey, I want to replace the order to 9996, so I know that a replace order happened at that level. You can also append other stuff, so Mongo is great because I can just say, oh, it's updated by algo 1. So now I know if a trader updated it, if the algo updated it, if some other system did it. And the key is that now that I'm only recording these events, think about it. I'm only appending to a table. This doesn't even have to be a database. We just write to a file. Who cares? The events are there. I can replay them back. But the real kicker is the current state system is held in memory only. And that's where you get all the performance benefits, because now I'm only doing one write to the database no matter how many objects I affect. Where in a CRUD-based model, I have to go and update the state of every single object. If there are 20 objects, I have to do at least 20 updates, right? 20 orders, 20 updates, plus some more, any trace that get generated. With event sourcing, I record only one insert. It's append. Mongo has already pre-allocated that space. It's going to be in memory. It's going to be fast. And then every other update only happens on objects in memory. Okay, so if you're following me, you're going to say, aha, what happens if we crash? Right. Okay, I got a solution for that. Let's just replay the events on startup to rebuild the current system state, right? It might look something like this. I'm going to go to the event store. I'm going to find, for a given market ID, so we partition our system by bonds because orders interact with each other. And I'm going to just loop through them, and then I'm going to actually apply the event that was called on myself. So I have this create order handler, I have this replace order handler, and then all the logic to rebuild the current system state is just going to be it's just going to be replayed. It's we've gone back through time, and then we fast forward just like a VHS tape. Just scrub through it. Okay. But what if we have a ton of events, right? I got 3 million of these things. So with event sourcing, what you can do is you can actually take snapshots periodically to create checkpoints for yourself. And a snapshot is just a background persist of the system state after n number of events. So every 10, every 100, however many you want to do. When you start up, you're only replaying from the snapshot, so instead of going through 1 million of them, you only go through a couple dozen. And what happens if you need to delete an event? Well, because everything is immutable, and once an event is recorded, we can never change it, we have to do a reverse offsetting transaction if we want to undo the effects of something. But this is kind of what we want. If someone goes in and they make a mistake, and for a certain period of time, no matter how long the system exists in this state, like, I kind of want to know about that, especially like when we're trading millions of dollars of bonds, right? For exactly 150 milliseconds, there was a glitch, and someone sent us an order that caused the market to wildly swing one direction, and then they went in, they canceled it, and now they're claiming that they got filled when the market moved to that level, and then we have to be on the hook to essentially get them out of that position. That's something that happens. It's, I guess Ian would tell you it's called an obvious error policy or something, right? So, there's a lot at stake here, so we really need to know, like, okay, well, what's a mistake? What exactly happened to cause that change? Did it just change, or did a trader accidentally change it? It's an external factor, whatever. And then how do I get the state of the system after an event? Well, this is where we kind of pull back that whole event emitter architecture and service bus. I can just sort of say, like, okay, I'm just going to notify whoever cares about it that, hey, this order was replaced. So now if I have other services that care about the fact that a username was updated, a credit limit was increased, an order was modified, they can just subscribe to it, and I can keep the logic of handling orders just like focused on the job of handling orders. And so how do we do this in Node? There's a library for that, right? And a shout out to Mateo Del Norte, whoever this guy is, probably like scaling the Andes of South America. Where is he? Oh yeah, he's like back there getting some pizza. Yeah, so Matt wrote these libraries, and we use them, and they're pretty awesome. And I encourage you to check them out if you're interested in this stuff. Okay, so what does it look like to event source? We have this idea of an entity. An entity is the thing that you're capturing. In our case, it's this market. The market has an ID, which is going to be the bond that it represents. It has orders in there. It has trades, right? And that was my definition from earlier. Market has orders. When two orders cross, they form trades. So the market is kind of like the thing that manages these other things, right? And it controls the interaction behavior between them. I simply inherit from an entity, and there I go. Then I have this thing called create order. Now if you look down here, when I actually get a create order, sourced is going to take care of persisting the event through this digest call. So essentially that says, hey, record the fact that create order was called with these parameters. And then what happens if I ever go down is just going to replay it. But the real magic is the fact that I'm just doing an insert to an in-memory array at this point. I'm not saving to any databases. So my order is going to exist in memory. It will be there for me to use and interact with. But I've only done one database right. So no matter how many times I change that order, at what point, it's like, it's pretty cool. So it gets a little more involved, right, but not too complicated. There's this idea of managing entities, and this is a little more complex because I want to show an example of how to cache these things in memory. So you have this idea of, okay, I have an entity, now I have a repository. The repository is the thing that saves and fetches the entity. So it's not actually pulling out the state, it's pulling out the snapshot, replaying the events, and then it essentially just delivers you a market at the end of the day. It says, cool, I'm just calling marketrepository.get, and now I have an in-memory instance of a market up to the current state. I put in a bit of the source code just to show like how simple it is. Like it's literally going to snapshots tables, finding it by ID, sorting it by version number, converting it to an array, finding the events, returning those things, and then iterating through them and just applying them to the object that you created. And then kind of to complete the picture, like using this service bus, right? I can listen for new commands. A command can be create order. The first thing I do is I get it out of the repo. It gives me an instance of the market, which is an in-memory cached version of it. I go and I apply my event to, or command to it, right? Market.create order. And then if there's any errors, I can reject the message, and what happens is that event never gets persisted. So the market effectively gets rolled back on the next transaction to the state that it was without any damage. And then if there is no error, then the repo commits it, and at this point, the event is saved in the database, and I'm good to kind of notify the world that, hey, something happened. And so that's, the notifications is kind of where it gets a little tricky, because inside the market, because I'm applying this event, I'm kind of like within a transaction, if you think about it. Like, I get the market from my repository, I'm applying these events to it, I'm applying business logic, and I don't want to emit events until I have that thing committed and stored in the database, because I don't want to tell the rest of the world that, hey, a new order was accepted, when, oh shoot, like 5 lines later, I throw an exception and I can't actually accept this new order, right? So what sourced gives you is this method called in queue, which says, okay, I want to notify someone that I've changed, but wait until after the commit to do it. So essentially it just queues them up, and then once the commit happens, it goes and emits all of your events. So you can use that same event emitter pattern. And the other thing that it does is during replay, it doesn't emit events. So as I'm like querying for events and blasting through them, I'm not like telling everybody, oh, hey, a duplicate order is created, right? So it maintains that concept of item potency. Okay, so now back to the CRUD example. So I have this event, sourced architecture, and the question is, cool, like, I don't need messaging to do it. I can build a REST API and I can still event a source express, but then the question happens, well, how do I tell the client about these things that have happened? And you've heard it earlier, the answer is to use WebSockets, right? Like that's what everybody's doing now. So yeah, let's use some WebSockets, and every time there's an event that occurs, let's just like feed that out to the client and tell them to update their state of the world. And this kind of leads into the next thing. How do we deal with the fact that a client might have a different view than what I maintain in my service? So this is the last part of the slides. You guys are champs. Thanks for being here. Any questions? Do you understand conceptually, like, it's, what's weird about it is like, I can't just like query a database and see what the current state of the market is. But what I can do is I can collect those events and I can save those events in a different database that kind of puts together a view that I would find useful as maybe an internal developer. And that's kind of what CQRS is. Question?
Yeah, question. Looking at something, maybe just a naming convention, but it looks like you're persisting commands.
Yeah.
Instead of like order place, you actually persist in place order.
Yeah.
Is it just for historical reason, or is it like underground logic?
No, it's sort of weird. Like, you call it event sourcing, but what you really want to do is like, you don't want to persist the fact that something happened. You want to know about the thing that caused all these series of changes to occur. Because think about it, I don't want to update the fact that an order was updated. I want to say, what was the thing that came in that caused the order to update? I mean,
well, if you replay, if there is any dependency on outside conditions like time or anything else, if you replay commands,
yeah,
you may get into different states.
That's right.
But not deterministic.
Well, and the interesting thing, we have that issue because when we trade bonds, some of them are benchmarked to U.S. Treasury, and we need to actually get the price of the Treasury in order to trade them. That comes from like an outside service, which I'll show you guys. When we get a new order, we actually have to update the state of the market to say, here's a snapshot of that Treasury, then go and process the order. So there's this idea of, if you're familiar with like domain-driven design, like these sagas and saga patterns where you kind of suspend your execution, you send something off on a quest and it comes back with some data, and then you resume it. I don't want to get too deep into it because it is kind of complicated, but yeah, I struggled with that. And I just learned to accept the fact that, it's really command sourcing, maybe, if you want to call it that way, you're persisting the commands that drive it. That's the way that we found works for us. I haven't looked at like Greg Young's implementation. He's the guy from Microsoft who started this whole thing in C#, and the idea kind of grew out of that, but it might be worth it to look into. They talk about this difference between commands and events. we'll get into that a little bit. Question?
You gave a really good answer as to why you chose Rapid.
Yeah.
Is there any reason because you're doing this playback on a crash, is there like a mind for not choosing Kafka for like replaying your event streams on a crash?
Kafka is the Java-based implementation of a thing.
Yeah, Kafka's really good at replaying like the stream.
Yeah. No, you know, like, we're all just kind of familiar with Mongo, and we trust it, and it works, and it does the job, and it's kind of one of those things, like, I haven't explored Kafka. A guy on my team has, and he was telling me about it, and I'm like, well, we have all these libraries that just work with Mongo. What's interesting, if you notice, there was a sourced repo Mongo. You know, I'm sure we could write a sourced repo Kafka, and that would be kind of an interesting implementation to do, right? So the question was, have we looked into Kafka versus Mongo for persistent commands? Anybody else before I go on? All right. We're nearing the end here, so bear with me on the CQRS stuff, because this is where it really gets kind of, you know, I thought event sourcing was wild. This is more. Okay, so in a single model, like the way that you model UIs is very much that like express-based architecture. You have this like web application, and you have a view into a database, and the data that you store is the data that you deliver to your clients, right? In CQRS language, or world, what you're doing is you have these like two different channels, right? You have a command channel. So what you're doing is you're firing commands off kind of into this, to your back-end core logic. Those commands are making a round trip, and then they're coming back through a read-only view of the new state of the system based on those commands that occurred, right? So it's not like you're doing request response. It's like fire and forget, and then, oh yeah, I'm eventually going to get an update to my UI. How does that work? Well, or why would one want to do it? The main reason is because in my service, like, you know, a view of an order is very simple, right? It has a couple of IDs. But like to a human, you know, I tried showing some of these IDs once, and like, you know, sales team came back at me and they're like, what are these things? Like, I don't know these numbers that you're showing me. Like, I want to see firm names, and I want to see my custom codes, and I want to like have nicknames for these accounts and stuff like that, right? So in a single model view, the way you do that is you persist all that stuff, and you have this like big like model of like 200 columns that like has all this stuff on it, right? Where you have joins that you have to do. But in CQRS land, what I can do is I can maintain totally separate views for my backend services for like processing and using the data. And then when I want to present it to the user, what I can do is I can essentially go out and pull in any additional information, and I'm going to actually, bear with me, duplicate some data and store it in a separate database for the purpose of using it on the UI. And the reason for this is because, you know, in like a domain like a trading system, you have traders, you have internal admins, you have reporting users. You know, you have like all these different groups that you're serving. Each person has this like different notion of what they care about on that data, right? An order to a trader is not the same as an order to like someone who settles these things. They need more information. They need like calculations and stuff. So the way that we do this inside of a microservice architecture in CQRS land is through this technique called a denormalizer. And it essentially is just another service. And what the denormalizer does is it just listens for events that are emitted from your services on the back end. And then it implements logic just to say, okay, the fact that an order was updated means that I need to now update the client's view of the order. So then it goes through and it can selectively choose what fields to update, or it can actually go out and fetch some more data in order to update it, right? And the reason why we do this is because the events are going to be coming from like all these different services. You asked about what was like our brain. Well, there's this market service that kind of runs everything, but there's also a treasury service, there's the account service, there's a credit service. And all these things like matter to the user that's operating the system. And so we need to build this like consolidated view, but I want to be able just to like work on the market independently from credit. You follow so far? The trade-off is that you're duplicating data. There's no way around it. I have different versions of orders floating around in the system that are being presented to different users, but I'm making the argument that that's actually okay, right? I would say that maybe the existing school of thought or the traditional school of thought is one source of data in one place, right? If you have an order, it's persisted in this table because making sure everything is consistent is too difficult. With this event sourcing pattern, these events are flying around, and so it's really easy to keep things up to date. You just kind of have to accept the fact that there's going to be some latency in getting those updates. Some things might get it before others, but that's kind of the nature of like how a financial trading system works. A computer is going to get notified of a trade faster than a human's eye, right? So I don't care that maybe the front end has a little bit of a latency, because that trader in no way is going to be able to compete with the speed of a computer and reacting to trade events. So it's fine that the UI takes maybe an extra couple of milliseconds to update. The cost is I have to duplicate some data, and some people just cannot get over that. They don't like that there's an order here and an order here. They have the same ID, but they have different fields on it, and I'm worried if I change that thing that it's not going to make it over here. And that's a concern, and that's really, probably the biggest thing that we're struggling with. Not struggling, but it's the thing that we have to build a lot of defense into. If something goes down or an update doesn't make it, right? You have to be able to go and repopulate. Yeah, question?
Can you talk about this generalized just keeping state in memory to basically replaying their projection out of the events and not storing it into a separate database? Would it work for you in this case?
Well, yeah, so the question was, have you ever considered just storing the denormalized view of the events, the client view model, just in memory and not actually persisting it to a database? Well, the nice thing about persisting it to the database is the fact that Meteor has this thing called built-in oplog tailing for MongoDB that automatically takes whatever you write into a Mongo, regardless of how it got in there, and it just it has the ability just to flush it out to a client. You have to set up some of the subscriptions and stuff like that, but what's incredible about it is that it's completely eliminated the need for us to have to write an additional API between the web app and the UI, like the people who develop WebSocket stuff. You have to create your own messaging SKU, right? Order added, order removed, order updated, keep track of sequence numbers. The reason why we selected Meteor was just for this reason. It's something that we could just stick in front of that client view model, and it transparently moves the data onto the browser, which is pretty awesome. Now, it's a little bit of work involved, but compared to all the design architecture needs we have to do, it's not a whole lot. So now that I've gone through that, let's demo again. What you're actually seeing here is a round trip all the way through our services and through a bunch of other services that's happening as fast as the eye can see. And just to kind of prove it to you, I'll show you how we develop these microservices. So I understand it's probably a little blurry. Tmuxinator is sort of this neat thing that we're using. When you have microservices, you have a lot of services, so you need to kind of figure out how to run the services all together. And so we have this cool command here. So I can kill the section, or the session, and then I can do make run. In a terminal, what it does is it automatically fires up these services and puts them in tiles, and these are our 4 web applications that we've written, and we have right now 8 or 7 core services, and then we have 2 API services that are running, and you can kind of look at the state of the system. So I was just working on this. I fixed our test suite so that it works properly now. I'm going to try to run a test for you guys so that you can see kind of the orchestration of everything flying back and forth. And there it goes. So essentially what's happening is the test suite is pumping these messages. It's sort of simulating like what a trader would do. And this guy over here with all the text is like our brain, that's the market service. And every time like something happens, this is the denormalizer, is pushing it up to there. This is the thing that updates the client. This is a credit service, so before a trade happens, it actually goes out, checks credit, records the fact that credit was used and returns it. And there's a couple like reference data services, treasury services. So all this stuff is like working in concert. And, ooh, look at that. All of them passed. Awesome. And just for the full effect, okay, well, what does Meteor give you? Well, okay, so I'm going to run this again. And the way that the test suite works is that it checks out against the denormalized view. So it says, I'm going to create an order. I'm going to make sure that it's in the client's view model database. So theoretically, Meteor should just be able to pick that up. So if I run through that again, you'll see that it's essentially like just going through like all these different states of the market using those two securities. And it's like testing all this stuff that could potentially happen. And it's like working in real time, like before your eyes. I just think it's so awesome that, and I didn't have to write one WebSocket or Ajax or anything like that.
Can you expand on your test suite a little bit? On what you did, what tools you're using?
Sure. So I believe. Yeah, so the test suite was actually one of the first things that I did when I joined the company. Amar and Ian had this idea that, we want the orders to interact this way in the markets, and they would give me like kind of an English description. So,
what about the text size?
Sorry?
Command plus.
Oh, yeah.
The text size.
So what the test suite actually does is it's written using Cucumber, but Cucumber.js, no Ruby in our platform, right? JavaScript. And what's cool about it is that these are actually the tests that are being run, and each one of these commands maps to a message that I'm just firing into the system. So I say, I want to test the case where a valid limit order is accepted. So given an empty market for this test QSIP, Trader 1 creates an order buy 1 million at 99.75. Then, then I'm doing my assertions. And what's cool about this is that you can just keep building on these building blocks. Like you can just create these, like all these weird situations. I have like 5 buys and 4 sells, and this thing changes, and what's supposed to happen.
But all your feedback is through the UI. What are you doing to test between, I don't know, clients and producers that don't affect your UI directly? How are you testing that?
Yeah, so an example there would be our fix engine. And our fix engine, so fix is the financial information exchange. It's like a protocol for brokers to use to communicate information. That doesn't go through the UI. The fact that an order was created shows up in the UI as an anonymous order, but there's like a different API. So the checkouts are different. What it does is, in the background, it initiates a subscription, and it listens for fixed messages, and it creates an in-memory array of all the messages received. And then the checkout is, did we receive a message with these parameters? And so, it's just the code behind, which is actually inside these things called step definitions. We just, it says, okay, create a new limit order. The order looks like this. Then we use our fixed client to send it. It gets fired off into the ether. Down below, what we do is these say 1, 1, 1. Okay. Then it should be a blank order, blank, 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 and there's all these kind of like status side QSIP. What we're doing is, just looping through an array of messages that we got back and say, did we get the message that we expected to get back?
Okay.
And so that has nothing to do with the UI. So it's like whatever part is like most customer facing, that's what we want to test, because those are the people who are going to call and be annoyed that we're system breaks. Any other questions? Yeah.
By using JavaScript
Oh man, yeah. Yeah, where's Nat? Yeah, okay. Yeah, so big number.js, right? Like that's kind of, we're starting to convert everything over to that. I would notice these weird things where inside the system I put it in order for, you know, maybe not this one, on one of these price-based ones, and it would actually be 91.1999999, and then you go to compare that, and it's actually off by like 1/16th of a penny, and so it doesn't trade, but the rounding comes back, and it's like, oh, I have this locked market. Why, why is that happening? So yeah, that's a big issue, and the way that we're going to handle that is just not do any division, multiplication of actual JavaScript floating point numbers. And what we'll do is we'll just convert everything to a big number.js from a string representation. Because everything in our system is fixed point. Like the highest precision we'll get on these markets is like a nickel. So we'll just send that down as a string and like parse it out, and we'll just know that we're actually getting 91.05 or 15. Right. Question was, have you run into any floating point issues? Answer is yes, a lot. Question? Yeah,
I have a Meteor question.
Oh, cool.
So how easy or difficult was it integrating Meteor with your microservices? Is there like a constellation of timescale with the packaging? How do you
The fact that I could build a denormalizer to set up the data exactly how I wanted to be consumed by the UI made it incredibly easy. It's just I just don't use any of the database write functionality in Meteor. So whenever I call something, right, I say create an order, it's always a Meteor method, it's never a database save. And then that Meteor method goes and it uses servicebus to fire off a message onto our messaging infrastructure.
So you're integrating servicebus with the...
Yeah, and that's on our open source page, by the way. Just kind of want to throw this up there. So we're on this rampage to really. It's a lot harder than you think to write a Node.js financial trading application. Not for like technical reasons, but because open source has like these weird sort of like legal and compliance ramifications if you don't use it correctly. And we've been trying to navigate that and stuff, but like FINRA has this rule where you have to have things pre-approved before you can like release any company advertisement. And we found out that like stuff on GitHub is sort of exempt from that, right? But it's not, they're not totally clear on these things. And so that's why I think like we see like a lot of banks and financial companies who are sort of like late adopters in this, because it's a lot of compliance work. The government has made it this way. They're saying you cannot advertise or post things on social media sites unless it's pre-approved by an officer of the company. And like everything that open source developers do is through like social media. This talk had to go through a compliance officer before I could give it. It's like it's a different world, but I think we're fighting it because it's a lot more fun to run services this way. And plus, I think it's like it's an entire industry that's so like relevant here in New York that like it's kind of been like stuck like 5 or 6 years in the past, right? Like Java, Enterprise Systems, Oracle, like these are the companies that are like running that game, and it doesn't have to be that way. Question?
Yeah, when you were talking about the denormalizing of your data, I would create a method using Mongo and stuff, look up other collections, stuff that data, and then send that over to you.
Yeah.
Isn't that your volume was too high for that?
No, it's just that by using Meteor, they've taken care of that for us. We don't need to do any of the sending. We initiate a subscription on one of those collections, and it just transports it for us. So it's effectively doing what I wanted to do. I just didn't have to write any code to do it. It just configures the code. Question?
In your event source implementation, what happens if there's a node that goes down or is unreachable but still has events that need to be fired, and then it comes back up and can now fire those events, and they're actually old events? And
Yeah.
how do you handle that scenario?
So the question is if you have events, that the node goes down that actually need to be fired because that thing was maybe persisted, right? And then it comes, like it just happened like between those two lines of code, the system gets out of sync. Yeah, that's that edge case that makes event sourcing a little bit difficult, right? The way that we're planning on handling that is doing some sort of like sequencing of events and like some sort of sanity check. So like if the denormalizer ever receives events that have like odd timestamps, like hey, I received an event after, like more than 500 milliseconds after I already committed an event like this, something got out of whack, and you know, let me just go query that service and see what the latest state is, and so I can update my UI view. You know, it's like thinking through, one of the most challenging things about event sourcing is thinking through all the ways that it could potentially fail. The library does a really good job because it doesn't fire any events until the transaction's been committed, but after that transaction's been committed, you have all these events that are queued up, your messaging server could go down, right? And then what do you do, right? Like, you know, there's these like little pieces, and you know, you just kind of have to accept the fact that no system is perfectly 100% resilient, and we need the way, what we're doing is we're building in the ways to detect that maybe something has gotten out of sync, and then to build in the tools to go and say, okay, we need to refresh something. Does that work? It's not a great answer. There is no great answer. Okay, question? Yeah.
Just had a question about the, it sounds like everything is in Mongo, but guaranteeing rights for the Mongo and like financial transactions.
Yeah.
How do you get around that?
Well, the transactions are all done in memory and in logic, so those are all guaranteed for us. It's the persistence of the event that caused that thing to be written, and the key is that we don't actually move on and start processing the next event until we've gotten notification, you know, we've gotten a write concern that says, hey, you're safe now, that event's stored, and it's okay to move on.
So through that source library.
Yeah, exactly. If there was a line called commit has a callback. Once you get that callback commit, that means your event store has been written, and there's no undoing it. You cannot go back and undo that event, even if you fail. You have to think of, how do I back out that event in the event that I need to, I say event a lot, but how do I back out that event in case if I need to somehow undo the effects of that transaction. But that's the beautiful thing, it's just an append only, there are no transactions. It's like, instead of pushing the transaction logic to let like the database manage for us, we've kind of like redrawn the boundary inside of our Node app. Like we kind of stuffed our Node app inside of the transaction boundary. So it's like every time a message comes in and we go to process a transaction, that object that we're operating on is locked, and nothing else can change it while we're in our single-threaded event loop, right? And that's what's so cool about it. It's like we've sort of like moved the lines in our favor. We have more control, make it faster. Yeah, question?
So the market service, microservices have a stateful thing that source all the events, keep state in memory.
Yeah.
So do you keep, like, is it how many services then? And if it's more than one, how do you route all this to?
Okay.
You have to route them, right?
Yeah, that's right. There are 2 virtual servers that this is running on. And each virtual server, I think we gave it like 16 cores or something like that. And the way that we do it is every market trades for a given bond identifier. So the QSIP of the bond. The way that we're doing it is that when you look at our queues and the way that they're set up, every order that comes in has to say a market. It's like impossible to trade an order without a market on it. So we know what the market is, and we just send that order to that market's queue. And then the way that the markets are set up is we have this little manager process that evenly distributes all the markets across the 32 worker processes that we have. And you know, if one worker goes down, there's this manager service that pings it every second to make sure that, oh, I'm getting responses from all the things that I think that are up. And if it ever detects someone's down, it shuts down those markets and essentially reopens them on the rest of the workers. So it kind of has this like live redistribution of you know, batching. Yeah, so but it's segmented by QSIM, and that's pretty common. Question?
Does the manager actually know what transactions are being processed by each market? Is there like
No.
a main table?
No. So it just, all it does is it says, hey, there's a worker, it's up. I'm just gonna keep telling orders, I'm gonna keep making sure that this worker is handling this queue. It essentially creates the bindings between the worker and the queue.
So what about anything that's on the order that,
Yeah,
like those, say there's 3.
yeah. Those events are persisted in RabbitMQ using guaranteed messaging. So they start up on a different worker, they pull them back down, and it picks up right where it left off. That's a good question. Yeah.
So all these questions about failover,
Yeah.
have you guys thought about, or are you guys looking into this replication or partitioning? So let's say orders for certain, let's say, bonds,
Yeah.
you get one service versus another one.
Yep.
What about that? And also just having 2 services running in case one of them fails over, and then there's an easy cutover to.
Yeah, the key is that, like, because we replicate the Mongo, like, we can have DR that way because we're gonna get, site-to-site replication, so that's cool. In terms of, like, processes going down and starting back up, our strategy right now is just to evenly round-robin load balance everything, so if a worker goes down, we'll just disperse whatever markets were on that worker across the rest of the live workers. We're thinking about something of like kind of having like a priority zone. So if there's like particularly busy symbol or QSIP one day, like we'll have the ability to like designate, say, hey, I only want this CPU handling like 5 QSIPs and the rest can handle, 250 or whatever the load is. So, we're toying around with that, but we haven't run into any issues that indicate that we really need to do that. So we're just kind of holding off on building that level of functionality until we, it starts to become a problem.
I think you can distribute in Rabbit that way, just by.
Yeah, they have different techniques, like there's high availability, like
Sure.
where you can replicate the queues across different nodes, or you can use it as like an in-memory node and a persistent node.
But even just time for a worker to process rather than doing round robin, it actually pays attention for when the act comes back.
Yeah.
Say, oh, okay, we just do more work on this node.
It's funny that is how we do it. So it just
Cool.
says,
So you're gonna get
if this
it.
worker responded and I don't
Yeah.
get a response in 3 seconds, I'm going to shut it down and I'm going to put the market somewhere else.
Okay.
And then when it comes back up, it will just have no subscriptions. Okay, so I guess my learnings from this whole thing of starting in March and getting to where we are now is there's a tendency to overcomplicate or overthink things. Like I'd say, keep it simple, solve for the problems that are on your plate. There's going to be so many things that you don't know that are going to happen that are going to happen. Don't use event sourcing everywhere. Like this was, you think you fall in love with something, you really think about it, you put a lot of effort into understanding it. For storing a table of bonds, like sometimes it's nice just to see those bonds there, and it's like only really where you're going to get business value out of having to maintain that event log. Migrating data is another issue that I really didn't get into, but if you change the way that your system behaves, how do you handle the previous events? We think we're just going to snapshot it and be like, snapshot, archive, it's there if we need it, but then we're just going to keep moving forward. Like, I don't want to maintain all this legacy code. I found what was really surprising is how decoupled CQRS makes the UI. Because there's like this barrier, like the view model is the view model, and I can write all my tests, make sure the view model is there. It's like our UI never breaks because we changed the database table. Like that almost always gets caught by a test or the fact that the denormalizer doesn't like that you're sticking a null value into Mongo, like it has that validation. And so like we have this very clean API that no matter what changes in the back end, the data that's presented to the front end is like specifically designed for that. So it's actually been a real huge benefit for us. And just like kind of like my main motto in development is like always be refactoring. Like when you write stuff, you're not going to get it right the first time, so don't try to do it. But know when to take the time out of your day. last night we had a problem with our fix engine, and so I said, you know what, I'm going to fix the test suite because I'm really bothered by it doesn't run cleanly. And you know, it paid off. I was able to demo it for you guys today, so that's good. So you know, thank you. We're looking to build our team with Node.js engineers, and check us out. We have some cool open source libraries. We have a quick fix wrapper for Node. We have Ian rewrote a whole bunch of bond calculations correctly in Python. That's hosted up there. Matt has his like Node Python project up there, so how we call Python code from within Node. And you know, there's a couple of Meteor wrappers for servicebus and some other projects, and we're going to keep updating that and really try to help the financial services community by putting some awesome JavaScript out there that creates more jobs and opportunities for all of you guys. So, thank you.